So we talked a little bit about what happens when a electromagnetic wave encounters a change of impedance. Some of the signal is transmitted through, and some of the signal is reflected back at the source. So what we're saying is if we've got an incident waveform traveling from left to right, and it's in some material with a characteristic impedance of Z1, and it reaches a boundary where it has a this new material has a characteristic impedance of Z2, what's going to happen is that reflected wave, some of it is going to get transmitted through, and some of it is going to get reflected. So we've got two components, the reflected wave and the transmitted wave. And what we want to know is, well, how big is this transmitted wave and how big is this reflected wave? What we'll see is that the difference between the impedances in the two boundaries will determine the amplitude of both the reflected wave and the transmitted wave. And this is quantified by a parameter that we call the voltage reflection coefficient. It is given the symbol uppercase gamma. So we write that. It's a phasor number. It's got a real and an imaginary component, so we can write it as a vector quantity. We put a bar on top of it. And the reflection coefficient is, it tells us that the amount of reflection is given by the percent difference here. So we've got Z2 minus Z1 over Z2 plus Z1. Again, as Z2 is the medium that the wave is transferring into, and Z1 is the medium that the wave is coming from. So this is called the voltage reflection coefficient, is its full name. And it has no units. It can be a complex number. Now, if you think about it, what is going to happen here? The wave is going to reach this impedance boundary, and either at one end of the spectrum, all of it's going to be transmitted through, or at the other end of the spectrum, all of it's going to be reflected. So the reflection coefficient tells us how much of it is actually reflected. So the minimum value of the wave that can be reflected is 0, and the maximum amount of the wave that can be reflected is 100%. So always remember that these reflection coefficients are going to range between 0 and 1. Reflection is independent of frequency. So you notice here that it's just dependent on the impedances of the two boundaries, which are not frequency dependent. It seems contrary to the belief that electromagnetic effects don't occur at low frequencies. And from this equation, what we see is that reflections occur at any frequency. It's only dependent on impedance differences. And what that is saying is that voltage reflections have actually been occurring in all the circuits that you've been measuring. It's just that the effects have been so small in previous classes that we haven't had to pay attention to them. As the lengths of the transmission lines get long as compared to the electrical length, this becomes more and more noticeable, and that's why we're studying it in this class. So now let's take that concept of reflection coefficient and apply it to a circuit. So here I've got a source generator. This might be a function generator in a lab, and it's got a source impedance associated with it as ZS, source impedance, right? The transmission line connecting the generator to some sort of load has a characteristic impedance that we call Z0, and that load has an impedance of ZL. In this circuit, it's possible that a reflection will occur both at the load and at the interface between the generator and the transmission line. We can find the reflection coefficients at these two impedance boundaries using the voltage reflection coefficient formula we showed on the last slide. And so we're going to call the first one the voltage reflection coefficient at the load, and that's going to be the impedance of the load minus the impedance of the transmission line, or characteristic impedance of the transmission line, ZL minus Z0, divided by ZL plus Z0. So that's the reflection coefficient right here. The second reflection coefficient, voltage reflection coefficient that we have in this circuit, is the reflection coefficient at the interface between the transmission line and the generator. And so what's happening here is we've got a reflected wave coming back. It's in ZL, it sees ZS, and then a second reflection can occur. So we've got the reflection coefficient at the source is equal to the impedance of the source, ZS, minus the impedance of the transmission line, Z0, divided by ZS plus Z0. So two different voltage reflection coefficients. At the impedance boundaries, both the voltage and the current are reflected, and what these are voltage reflection coefficients. It turns out that the current reflection coefficient is just minus gamma L and minus gamma S. So these are current reflection coefficients. And I will say, although this number can be complex, gamma L, gamma S, for either a voltage or a current, very typically we don't note it as a vector. So although gamma is technically, of the form A plus JB or real plus J imaginary, and therefore should be noted as a vector, a lot of times that's dropped off and we just write it as gamma. So I want to make some observations about this circuit. For a lossless transmission line that's delivering a signal to a resistive load, maybe write those conditions down. Lossless T-line to resistive load only. Lossless implies that there is that the Z0, which is normally complex, R0 plus J X0, it implies, if it's lossless, it implies that that the characteristic impedance is purely real. And if we're delivering to a purely resistive load, ZL is just purely real. The characteristic impedance, or the reflection coefficient gamma, is going to be RL minus R0 over RL plus R0, and that has to be a real number. And what that indicates is the voltage waveform, when it hits the impedance boundary, it just gets reflected. There's no phase shift occurring because there's no imaginary component to the reflection coefficient. So that's a very common case. Another case I want to point out is when ZS equals Z0, or the case when ZL is equal to Z0. These are called matched conditions. That's a matched generator. The source is matched to the characteristic impedance of the transmission line, and this is called a matched load. The load is matched to the characteristic impedance of the transmission line. And in both those cases, the reflection coefficient is going to be Z minus Z over Z plus Z, which is just 0 over 2Z, which is 0. So at a boundary that has a matched impedance condition, if ZS is equal to Z0, no reflections occur at that boundary. If ZL is equal to Z0, no reflections occur at that boundary. And that's very, very common in electromagnetics, is that we can eliminate reflections by matching the source to the characteristic impedance of the T-line and the load to the characteristic impedance of the T-line. If all of them, if ZS is equal to ZL is equal to Z0, we call that a matched line. And there is no reflection at all. No voltage reflection, no current reflection. So no reflections occur. Gamma is 0. Go back up here. So if we're looking at the reflection coefficient at the load, if the reflection coefficient at the load is equal to 0, there's no reflected wave. That means all the voltage getting to the load, it only takes one cycle for that to happen. And so the T-line is charged at T equals whatever the length of this T-line is. We'll call it D. Right? So the reflection, all the voltage waveforms, since there's no reflection, must meet the load after one travel. If the reflection coefficient at the load doesn't equal 0, but the reflection coefficient at the source does equal 0, what happens is a wave is generated from the generator, it travels down the transmission line, it's reflected by the load, but no return wave is reflected, and therefore the transmission line is fully charged after T equals 1 cycle, 2 cycles, T equals 2D over mu sub P. If neither the reflection coefficient at the load or the reflection coefficient at the source equals 0, then what happens is a wave is launched, it gets reflected. The reflected wave is launched, it gets reflected again, and this wave bounces back and forth, back and forth, back and forth. From our boundary conditions, that might have been the last slide. From our boundary conditions for the reflection coefficient, each bouncing of the wave diminishes its amplitude, and so this wave bouncing back and forth gets smaller and smaller and smaller. But what happens is we get all these incident waves that add up together, and it creates something that's called a standing wave pattern, which is something that we'll develop more in a later lecture. But I just want you to be aware of why the standing wave develops. It's these additive reflections or constructive and destructive interference of these waves that are bouncing back and forth.